Welcome to the lecture on coding of NQueens problem. I strongly recommend you that you should watch the 4 parts of introduction to backtracking before you continue with this lecture. In the earlier lectures on backtracking, we have seen what kind of problems are solved by backtracking, what is the principle of backtracking, and how backtracking explores the state space tree. Now in this lecture, let's see how the problem solving methodology, which we have seen in the previous lectures, can be coded. We have seen that in backtracking, we started the root node of the state space tree, which is at level k equal to 1. And at any level k, we choose a value of xk and create a child corresponding to the value of xk. What would be the value of xk? The value x on xk can take on depends on the explicit constraints of the problem. In case of 4-queen problem, xk can take on the values of 1, 2, 3, 4. Of course, in 8-queen problem, xk can take on the values of 1 to 8. After we construct the child defines a partial solution of the problem. This partial solution is then tested whether it satisfies the bounding function or not. If the partial solution satisfies the bounding function, then we make the newly created child node as the E node and we recurse. We recurse in the sense we repeat the same process. Of course, if the newly created child node and the partial solution defined by the newly created child node does not satisfy the bounding function, then we choose the next possible value of xk and repeat the process. Now let us just refresh how the principle of backtracking is applied to the 4-queen problem. And as we refresh upon the principle of backtracking, let's also see how this principle can be converted into code. To start with, the root node is the E node. If you remember, E node is the node that is being currently expanded. And let's suppose that the function which we are coding is NQueens. The name of the function is NQueens, and it takes one parameter, and the parameter is the level. So initially, the NQueens function is called with the k value of 1. So because we started at k equal to 1, we choose a value for x1. So the first value x1 can take on is 1 in 4-queen problem, and we create a child node. This child node defines a partial solution, and this partial solution has to be stored somewhere. So presently, the partial solution consists of only one value, the value of x1. So it is stored in a global array x, which is the solution array. What should be the size of the solution array? The size of the solution array depends on the value of n in the NQueens problem. So in 4-queens problem, the size of the array should be 4, and in 8-queens problem, the size of the array should be 8. However, when it comes to coding, if you choose C or Java as programming languages, we know that the indices of the array begin at 0. So to avoid the location indexed with 0 and to work with the locations 1 to n, what we do is we create an array of size n plus 1 so that the location indexed with 0 is not used, and we will use the locations from 1 to n. So now, after choosing the value of x1 equal to 1, we store this value in the location 1, x of 1, and apply the bounding function. The bounding function quite obviously will return true because the solution satisfies the bounding function. Now, what is the next step to be done? The next step to be done is to recurse. To recurse in the sense, we call the NQueens function once again with the value of k equal to 2. So this node becomes the E node, and we call NQueens with k equal to 2. Now, before we look at the further aspects of solving the problem using backtracking, let's try to convert this portion which we have seen so far into the code. Now we know that at level k equal to 1, x1 can take on the possible values of 1 to 4 in the case of 4-pin problem and 1 to 8 in the case of NQueen problem. Or in simple, it can take on the values from 1 to n. So if x1 has to take on the values from 1 to n, we have to use a for loop. And we know that these values 1 to 4 or 1 to 8 correspond to the columns in which the queen is placed in the first level or in the first row. So we define a for loop with the variable call, which represents the column value and which changes from 1 to n. And for each column value, the value is stored in the location x of k because xk assumes all these column values one after another while the state space tree is being explored for the solution. So as a result, we have the statement x of k is equal to column. Currently the value of column is 1, but at a later point of time the column value can be 2, 3 or 4. Now once we store the column value in this solution array x, this solution array is then sent to the bounding function to test whether the partial solution satisfies the bounding function or not. So because this is a global array, we don't need to send the array itself to the bounding function, but however, we send the value of k as a parameter to the bounding function. What does the value of k represent? The value of k represents the length of the partial solution. For the time being k equal to 1, so the length of the partial solution is 1. At a later point of time k can be 2 or k can be 3, which represents the partial solution x1, x2, x3, xk. So if the bounding function applied on the partial solution, which is stored in the array x in the locations 1 to k, satisfies the bounding function, a value of true is returned, and if the value of true is returned, it recurses, means it calls the NQueen function with the next value of k, that is k plus 1. So the value of k will be 2 in the next recursive call, and the function gets executed now with the value of k equal to 2. Please note down that this is not a new for loop. Instead, it is the for loop that is present in the NQueen function, which is being currently executed now with the value of k equal to 2. And because we have chosen x2 equal to 1 to start with and created a child node, this value of x2 is stored in the solution array in the location 2. So x of 2 is equal to 1. And this E node defines a partial solution x1 equal to 1 and x2 equal to 1. You can see the same in this array in the locations 1 and 2, or from 1 to k we have the partial solution 1, comma 1. Now, the bounding function is applied on this partial solution, and we know that the bounding function returns a false value. Once again, this value of k, which is currently 2, represents that the solution is available in the locations from 1 to 2, or in other words, from 1 to k. Anytime the partial solution is available in the locations 1 to k, and that value of k is sent as a parameter to the bounding function. And of course, the array need not be sent because the array is declared as a global array. Now the bounding function returns a false value, so this NQueens function call is not made. So that completes the execution of the if statement, and the next statement that would be executed would be to go back to the for loop and execute the body of the for loop with the next value of call. And what is the next value of call? The next value of call is 2, which means that a node is created now with the value of x2 is equal to 2. Of course, this shows how the value of x2 equal to 1 does not give a partial solution which satisfies the bounding function, and the solution space is pruned, and we move on to the value of x2 equal to 2. So we see that the previous value of x of 2 equal to 1 is overwritten, and a value of 2 will be stored in x of 2. So now the partial solution is 1, comma 2, because x1 equal to 1 and x2 equal to 2. Once again, this node defines a partial solution, and the bounding function when applied on this partial solution does not satisfy the bounding function, and hence it is killed. So because the bounding function returns a false value here, this NQueens call with the next level is not called, and it goes back to the for loop and continues with the value of x equal to 3. So x2 equal to 3 rather. So x2 equal to 3, as a result of which this node is created, and this value of x2 is stored in x of 2 location. You can witness how the value of x of 2 has changed from 1, then 2 and 3, because you are trying all possible values of xk, and if the child node that is created as a result of a particular value of xk does not satisfy the bounding function, then it is killed and we move on to the next value of xk. So now the value of x2 in this for loop is 3, and the solution satisfies the bounding function, and hence this newly created child node becomes the E node. So if the bounding function satisfies, or rather the partial solution satisfies the bounding function, we know that this if statement will result in a call NQueens of k plus 1. That is, NQueens should be called with k equal to 3, and in that function we will choose the value of x3. So let's see. NQueens is being called with k equal to 3, and once again this for loop starts executing from call equal to 1 to call value of n. And to start with, x3 value is 1, and because the value of x3 is 1, this value is stored in the location x of 3. And once again, this child node defines a partial solution 1, 3, 1, which can be seen in the global array x 1, 3, 1 stored in the locations 1, 2 and 3 respectively. Once this node is created and this node defines a partial solution, we apply the bounding function on this. This if statement applies the bounding function on this partial solution which is stored in the global array x, and k is a parameter to that function. What is the value of k? The value of k equal to 3, which means that the partial solution is available in the locations 1 to k, that is 1, 2, 3. Now the partial solution is applied to this, and this partial solution does not satisfy the bounding function. So this returns a false value. Because this returns a false value, NQueens is not called. It goes back to the for loop, and the for loop executes the body of the for loop with the value of call equal to 2, which means x3 now takes on the value of 2. So x3 equal to 2 now. Now x3 equal to 2 once again defines the partial solution 1, 3, 2. You should observe that the value of 2 is stored in x of 3, or in other words, value of 1 which was earlier in the location x of 3 is overwritten with the value of 2. And once again, the resulting partial solution does not satisfy the bounding function, and hence this node is also killed. So if we continue like this, we realize x3 equal to 3 and x3 equal to 4. These two values also result in nodes or partial solutions which do not satisfy the bounding function, and hence these nodes are also killed. This is the board configuration corresponding to x3 equal to 3, which violates the bounding function. This is the board configuration which corresponds to the value of x3 equal to 4, and it violates the bounding function. So now, at this point of time, you should realize that this for loop is completely executed. It completes its execution. If it completes its execution in the NQueens function, then NQueens function called with a value of k equal to 3 should return to the point where it was invoked. Where was it invoked? It was invoked in the call NQueens of k equal to 2 with the value of x2 equal to 3. So now because the value of x2 equal to 3, this NQueens of k equal to 3 has returned. So the control comes back to the NQueens function, which was previously executing with k value 2 and column value equal to 3. So when it resumes, the column value equal to 4, and accordingly a node is created with x2 equal to 4. So we see that now the value of x2, which was earlier 3, now is overwritten as 4. And of course, we don't talk of the location x3 now, because backtracking has come to the previous level and it started exploring other possible values of xk. So x2 equal to 4 now creates a node, and this defines a partial solution, and this partial solution is once again sent to the bounding function to find out whether the partial solution satisfies the bounding function or not. Remember, the value of k equal to 2 now. So the partial solution is available in the locations 1 and 2, and this partial solution is now tested by the bounding function. So I would stop here tracing the backtracking process, because by this time you might have understood the sense of this for loop, how this for loop captures the principle of backtracking. So here the bounding function is applied on the partial solution and it satisfies, and NQueens should be called with the value of k equal to 3. So we'll stop there, because by this time you might have understood the importance of the for loop in the backtracking function NQueens, which is invoked with the value of k. Now let's focus on the bounding function. As I said, the bounding function always takes the partial solution which is available in the locations 1 to k. Here I have shown a snapshot of the partial solution which is available in the locations 1, 2, 3, which means that the value of k equal to 3. Now, how should the partial solution be tested by the bounding function? We know that if we have called the bounding function with k equal to 3, the partial solution corresponding to k equal to 2 might have already satisfied the bounding function. So our job would be to find out whether this value of xk2 in combination with the values of x1 and x2, does it satisfy the column constraint and the diagonal constraint? So you should check whether x1 and x3 satisfy the column constraint and the diagonal constraint. And after that, x2 and x3, do they satisfy the column constraint and the diagonal constraint? If at any point of time the constraints are violated, we return a false value. So we see that we take the values from I is equal to 1 to k minus 1 and find out whether x of I and x of k satisfy the column constraints and the diagonal constraints. So x1 and x3 are tested for column constraint and diagonal constraint. x2 and x3 are satisfied by the column constraint and diagonal constraint. And of course, I would like to once again remind you that the column constraint says that xi should not be equal to xk, and the diagonal constraint says that the absolute difference of I and k should not be equal to the absolute difference of xi and xk. So as a result, we have a simple for loop here for I equal to 1, I less than k. That is, we are looking at the partial solution values from 1 to k minus 1 locations. And then check each of xi with x of k for column constraint and for diagonal constraint. So if column constraint or diagonal constraint is violated, then we return a value of 0. If this for loop satisfies the column constraints and diagonal constraints for all the values of xi from 1 to k minus 1, then it's obvious that the partial solution satisfies the bounding function. And when we come out of the for loop, we return a true value indicating that the bounding function satisfies. Rather, the partial solution satisfies the bounding function. And then finally, the last part of the coding, how to find out the answer node. So far, we have seen how to recurse and we have seen how to design the bounding function. But when do you find the answer node? When do you print the solution? This is the for loop, what we have coded, which recurses at different levels. And we should somehow find out where should we be able to find out the answer node. We know that the answer node should be available when we have expanded at level k equal to n. So if the node created at level k equal to n by choosing a value of xk satisfies the bounding function, then it's an indication that the resulting node is an answer node. So we identify that after we know that the bounding function satisfies the partial solution and the value of k equal to n. If the value of k equal to n, it means that you have found out the value for xn also, and the value of xn is the one which is to be found at the last in the complete solution of the NQueens problem. So we find that if bounding function of k is true, we check whether k equal to n, and if k equal to n is satisfied, then we print the function. Otherwise, we know that we are at an internal level, we did not reach to the nth level, and we call NQueens of function. Let's move on to the actual coding part. Now, what shall we use to code? So I have a simple solution. Let's do coding online. We have a lot of online coding environments. So online GDB is a simple one for coding. So let us choose online coding environment. So, as I said, online GDB is one of the online coding environments. So let me search for online GDB. So I click on online GDB. So it gives me a very simple interface, which is very intuitive, easy for coding and testing your code. So I'll make the window larger. There are a lot of programming languages available, and let's choose C programming language. And let's do incremental coding. We take top-down approach. We start with the highest level function, and whatever other functions are needed in that, we'll keep coding them. So hash include stdlib.h is one header file which we will include. You should have guessed by this time why do we need this header file, because we need ABS function while checking the diagonal constraints. And then we define the constant n, which determines the size of the problem. And to start with, we define n as 4. Of course, you can run the program by changing the value of n to 8 or 5 or 6 or 7 to find out the solutions for other sized NQueen problems. And we should have a global array to store the solution. So we declare an integer global array of size n plus 1. You should remember well why we have declared this array as size n plus 1, because we do not work with the location indexed with 0. We want to be natural with the vocabulary of the problem, levels 1 to n. And to start with, let us design the highest level function, NQueens. So it's a void function, void NQueens, which takes level k as the parameter. Now in this, there is a for loop, as we saw earlier, which explores the state space tree breadthwise. And in the for loop, there is a recursive call which explores the state space tree depthwise. So you see that for loop helps you in breadthwise exploration, and recursive call helps you in the depthwise exploration. But that is the secret of implementing backtracking. So we have a local variable call which can take on the values from 1 to n in the for loop. So for call is equal to 1, call less than or equal to n, call plus plus. As soon as you choose a value of xk, we store that value in the location x of k. So the column value chosen will be stored in x of k. And then once you choose a value of xk, indirectly you are creating a node, and that node defines a partial solution, and that partial solution is sent to the bounding function. So we send the partial solution to the bounding function, but the bounding function needs only the value of k. It does not need the array containing the solution, because the array is global. And at this point of time, we also said that the answer node can be caught here. If the value of k is equal to n, then it is the answer node. So we print the solution that is present in the global array. We'll see the print function at a later point of time. And if the level k not equal to n, then we recurse. So we call NQueens function with the next value of k. I think that should complete the coding of NQueens. Let us just run through it. We have declared a column variable which takes on values from 1 to n. As soon as we choose a particular value that is stored in x of k, and then we invoke the bounding function to check whether the partial solution defined by xk, that is x1, x2, xk, is satisfied by the bounding function. Then if it is satisfied, we check whether we have reached k equal to n. K equal to n, we print the solution. Otherwise, we recurse. That should be all right. If there are any other errors present, we'll see at the time of compilation. Now let's code the bounding function. The bounding function should return a value of 1 or 0. It takes k as a parameter. So if the bounding function finds whether x of I and x of k satisfy the column and diagonal constraints as the value of I is changed from 1 to k minus 1. So we declare a local variable I, and then we run a for loop where I assumes the values from 1 to k minus 1. And then we check whether x of I and x of k satisfy the constraints. So first column constraint. If x of I is equal to x of k, then the column constraint is violated and we return a value of 0. Then the diagonal constraint. If the absolute difference of I and k is equal to the absolute difference of x of I and x of k, then the diagonal constraint is violated and we return a value of 0. And finally, we return a value of 1 if all the values of x of I and x of k satisfy the column and diagonal constraint. Now let's code the print function. The print function is a very simple one. It should print all the values available in the solution array x from 1 to n. Let me just increase the scroll the window so that we'll be able to see the code. So we should have a local variable I which runs through the indices of the solution array for I equal to 1, I less than or equal to n. We print all the values one by the other. And then finally, we print a new line character so that each solution appears on a different line. So that should complete the print function. We already coded NQueens. And now let's call the NQueens function. With the value of k equal to 1. So I'm not annotating the output by writing the possible solutions and all. You can just look at the solutions, and if this code is running, then probably you can add a few more add-ons to this program so that this program looks more elegant and gives you a more elegant output. Let's start running the program. There are errors. I find an error here, the semicolon missing. So let's see any other errors are there. A equal to n seems to be an error because n is uppercase. Okay, let's once again run so that oh, that gives us the solution. The solution, there are two solutions. The first solution is 2, 4, 1, 3. First queen is placed in the column 2, second queen is placed in column 4, third queen is placed in column 1, and the fourth queen is placed in column 3. In fact, that is the first solution what we got while we were solving the problem in our lecture on Introduction to Backtracking. And I encouraged you to continue the solution and find out any other possible solutions are there. In fact, this is the second solution. The second solution is 3142. So this also satisfies the constraints of the problem. No two queens are under attack. So that should complete the coding of NQueens problem, and that should have fairly given you a good idea of backtracking, with the principle of backtracking, how to solve NQueens problem using backtracking, and of course, how to code NQueens problem using backtracking. Now you have the option of running this program with n equal to 8, and I find a lot of solutions are there for n equal to 8. So you can explore more into this and try to get a thorough understanding of backtracking and how to code backtracking. Coding of backtracking involves a standard template. You have a for loop which takes you through the breadth-wise exploration, and a recursive call in the for loop which takes you to the depth-wise exploration of the state space tree. Thank you. We'll end this lecture here.